Okay, today we are talking about Hempel again, of Hempel and Oppenheim fame. Uh, Same person that came up with the deductive nomological account of the explanation also has an account for statistical explanation, right? And we'll explain what that is. So today we're talking about sort of explanation that happens when you're dealing with probabilistic laws. So a lot of our scientific knowledge is probabilistic in form. An example that Hempel uses a lot, and so we'll use it as well, is uh, antibiotics and infections, right? So if you have a bacterial infection, I give you antibiotics, you're very likely uh, to get better, right? The antibiotics are very likely to clear up the infection, um, but not every single time, right? Once in a while, people don't get better. So you can compare this sort of law to the kinds used in sort of Newtonian physics, right? So it's not like when I drop my phone, right? This tried and true example now, that like almost all the time it falls to the ground, but once in a while it doesn't. Um, or if for some reason it didn't, um, there would be some explanation for that, right? Someone would have had to like catch it or something like that, or I would have to be in space, right? So in general, laws in physics, at least to the Newtonian kind, are exceptionless. Um, So these are distinct kinds of laws. But just because a certain kind of law is probabilistic doesn't mean it's not incredibly useful, right? It's very good to know that if you have an infection, you have a very good chance of getting better if you take antibiotics, right? That would lead you to want to take antibiotics. We're currently dealing with a pandemic, right, of the disease, and as far as we can tell, last I heard, it had about a 0.01 probability of being fatal if you were infected with it. Of course, it's going to be different if you're in a different age group and stuff. Um, but that is very valuable information, right? It helps you determine how to live your life, right? You'll go out with a mask and you'll still go to the grocery store. If it had a 99 0.99 probability of being fatal, then you might reevaluate your behavior. So again, useful information. So the question is, how do probabilities factor in explanations? And this requires a different account. So just as an aside, you might, and some people do, question whether laws could ever be truly probabilistic, right? Whether explanation could be truly probabilistic. You might think the only reason that we can't get more specific, right, and make more definite predictions is just because we don't have all the information, right? You might think if I had all the information, right? So if I knew every part of your body and exactly how many sort of individual viruses were in your body and everything, and I also had laws that were like good enough that could predict the behavior of each of these, then you might think, yeah, I could actually say for sure whether you would survive or not if I had all the info about what's going on in your body. Um, that might be the case, right? Like I said, if I drop the phone and it doesn't hit the ground, usually I can get in there and I can explain what happened. Like it must have been a tornado or something, right? Happened. Um, so some of these probabilistic laws, um, it might just be that we just need to know more, and if we knew more, they wouldn't be probabilistic. And that's one possibility, but it's also possible that there just is fundamental indeterminacy in nature. And so far, our best account of what goes on with subatomic particles is that there is actually sort of fundamental indeterminacy in nature. Over on the right here, we have these wave functions, and these little sort of like fuzzy clouds are sort of like functions of where you'll probably find a particle if you do an experiment where you can observe it, right? But basically, the idea in the standard interpretation of quantum mechanics is until they're observed, particles are not in a determinate place, right? And it's not an issue of like, we just don't know where they are. It's an issue of they're literally not in any particular place at once, right? But either way, statistical laws do the job that we need, right? They help us predict phenomena. Um, in the case of probabilistic laws, um, our predictions aren't going to be 100% correct, but they'll be pretty good. Um, and that's good enough to, again, help you cure diseases like most of the time, right? So like, it seems that some of our greatest achievements of science are accomplished with probabilistic laws. So Hempel actually divides accounts of statistical explanation into two types. There is deductive statistical explanation, um, and there is inductive statistical explanation. Um, so deductive statistical explanation will have probabilistic laws. It will be deductively valid, just like DN explanation. Um, but what happens is your conclusion will also be probabilistic. So here's an example. Um, right? So if we have a antecedent condition that John has a bacterial infection, we have another antecedent condition that John is given antibiotics, and then we have a law that says people with bacterial infections who are given antibiotics recover with a probability of 0.9. So right, 9 out of 10 times they recover. Um, we can conclude John will recover with a probability of 0.9. That is, there's a 0.9 probability that John will recover. Okay? We can't conclude on this account of statistical explanation that John is guaranteed to recover, right? We can't make that statement. We're going to conclude a probabilistic statement. And what that means is that in an individual case, um, this conclusion can't be justified, right? Or justified. It can't be falsified, right? So if John doesn't recover, that's still consistent with the conclusion, right? All we said is he's very likely to recover. So that might be a problem if you think that being falsifiable, right, is the hallmark of being scientific, as Popper seems to think. So the other type of statistical explanation, according to Hempel, inductive statistical explanation, will allow us to conclude something more definite about John. We can conclude that John will recover, even though we're working with probabilistic premises. Okay, how does this work? So uh, the premises will be the same, right? John has a bacterial infection, antecedent condition. John is given antibiotics, another antecedent condition. We have our same probabilistic law. People with bacterial infections who are given antibiotics recover with a probability of 0.9. But instead, this time, instead of concluding that John will probably recover, or very likely recover, we conclude that John will recover. So what we have here is an inductive leap, right? Our conclusion says more than our premises say. This is not deductively valid. Um, and you might think, well, how is this explanation, right? If it's not deduction. And Hempel says, well, it still gives us a reason why you would expect the conclusion, right? So if I had those three premises and and I was to bet money what will happen to John, right? I would bet he will recover. Um, so you can still make predictions based on the premises, right? And based on the explanans. And for Hempel, that's good enough for explanation. Okay, so that's the big picture, and we'll spend a little more time on those two types of statistical explanation. Right now, we're going to zero in on some more of the details so we can actually get a more formalized account of what Hempel's saying. Okay, so more on statistical laws. So these will take the form of probabilities, and here's a little notation. Some of you may have already dealt with probability theory before. Hempel's notation is a little different than you've probably seen in your textbooks. So in your textbooks, you probably see something like P parentheses G and then the line and then F equals something, right? And Hempel uses a comma instead of the line. It's just an older, I guess, sort of notation. But in either case, what that little equation means is that the probability of a given F being G is R. And again, I think I mentioned this in our lecture, and we'll use this sort of terminology throughout this course in the readings. When we say an F is G, that's a variable. So it's something like the probability of a swan being white, right? Or the probability of a person um, with a person with an infection recovering, right? Things like that. Um, so this is a conditional probability, right? If you were familiar with those terms. Um, so in our example, the antibiotics, being given antibiotics A, um, giving called recovering from the infection R, right? And say that this sentence right here on the bottom says that the probability of recovery, right, given that you have received antibiotics, will be 0.95. So 95% chance of recovery. And again, I don't know if I said this, but yeah, if you're not used to probabilities, they're a number between 0 and 1, and it basically, if you see a 0.95, that means 95% chance that things will be fine. For the purposes of this course, that'll be fine. Okay. So here's an example of a statistical law in physics, right? So it talks about the half-life of radon, which is a radioactive element. So the idea with radioactive substances is they're unstable and they sort of randomly lose particles over time and gradually morph into a different kind of substance. They'll become lead or some other heavy element after they've lost all their electrons that want to fly off particles. So the process is probabilistic in that we can't, for any particular particle, we can't predict precisely, right, when it's going to fly off the atom. But we do know the half-life, and that is the period of time it'll take for half of the radon atoms in a given sample to decay right into something else. So for radon, the half-life is 3.82 days. So for a given radon atom, there's a 0.5 probability, 50% chance that it will decay within 3.82 days. So this is the kind of law that we use. Compare this with sort of laws you might see in a deductive nomological explanation, right? So here we've got some laws involved in gases, right, expanding when they're heated. So in the deductive nomological laws, instead of being in a probabilistic form, this is a universal generalization, right? So again, that x in parentheses means for all x, right, for anything whatsoever. And then the fx means if it's an f, whatever, if it's a swan, arrow, then gx, it'll be white, right? So this is for anything whatsoever. If it's a swan, then it'll be white, right? Or whatever else you want to plug in there. So let's take the law that any gas expands when it's heated under constant pressure, right? So call something is a gas, call it SX. Something expands when it's heated, call that EX. Then you get a law of the form for anything whatsoever. If it's a gas, then it expands when heated under constant pressure, right? And that doesn't have exceptions, right? There's no probabilities involved. It will happen, right? Okay. And he points out that probabilistic and deterministic laws, the reason you can say, one of the reasons you can say that they're both laws is that they're completely general, right? So there could be an infinite number of F's and G's, and potentially infinite number of bacterial infections, right? And they get cured and so on. It's going to apply to all of them. And this is kind of important sort of on a deeper level when we think about probabilities. And in the readings and stuff, they always do get in, there's like some deep debate about the nature of probabilities, right? And I've kind of tried to skip over that in the readings because I don't think it's not necessary and it gets kind of funky. But Hempel gets into it a little bit here. He says, look, these probabilities can't be about particular objects or like finite conjunctions of objects because then they wouldn't be laws, right? So laws have to be totally general. And they're not talking about just about the gases we've observed so far. They're going to talk about all gases, right? Present, past, and future. And this is the same for statistical laws. So as an example, take this four-sided die, right? We don't usually run these four-sided ones unless you're like a D&D player or something, but the probabilities are very simple. Right? So even if I never threw that dice, right? I just had it and it was a special dice that was owned by someone famous and I just kept it in a glass case and I never once threw it, we can still say that the probability that it would land on 4 would be 0.25. Right? You got a 1 in 4 chance. right? So again, the point being that these laws don't, these probabilities aren't sort of generalizations from like um, dice we have thrown. They're supposed to be about the dispositions of objects, not their actual behavior. Right? So we can make counterfactual claims. If I threw the die, then there would be a 0.25 chance that I would get a 4. I get a sort of a fine point, and we're not going to get deep into this stuff, but Hempel brings it up, and it's worth talking about a little bit. Okay. Now, not all statistical laws will necessarily have a probability statement of the probability of G given F equals whatever. Um, there are other kinds of statistical uh, concepts or the word I'm trying to use, I guess statistical concepts that will be invoked in these laws. So, for example, mean kinetic energy. Um, that's statistical in nature. You're taking an average of things, right? So that also counts as statistical law. Right here we have a law over on the right involving right average kinetic energy, right? Not the kinetic energy of a particular molecule, but of the average over a gas. Right? So that also counts as statistical law. And so a statistical explanation will be any explanation that makes use of at least one statistical law. And we have the two kinds that I mentioned, deductive and inductive. Right? And again, just to reiterate, the deductive kind, right, the conclusion will be probabilistic, and the inference will be deductively valid. So, one, the probability of a fair coin landing heads is 0.5. The probabilities of tossed coins are independent, so that means every time I toss a coin, it's always going to be 0.5 probability that it lands heads, no matter how many times I tossed it before or after, right? And therefore, the probability of a fair coin landing heads after a sequence of tossed coins is 0.5. So deductively valid, this is a little argument that sort of refutes the gambler's fallacy, where you think, oh, I bet, right, you're playing craps in the casino and you're like, oh, I'm due for a win, man. I've got, right, you've got to think, well, over the average, over the long term, I've got to win, and I've lost 5 times in a row. So this hand's going to be the good one, right? That's actually a fallacy. Every single time you throw the dice, same probability every time, right? Another example of a deductive statistical explanation, given the probabilities that we mentioned involved in the decay of radioactive materials, you can deduce the probability of a given interval of time elapsing between emitted particles being detected on a screen. That's sort of how you can tell if it's decayed or not. You have sort of a screen that will pick up, right? That you'll see if like an electron hits it. So you can deduce, okay, there is a point, right, 5 probability that we'll see a hit in the next 3 hours or 3 days, something like that. Okay, now on to inductive statistical explanation, which is really what he spends most of the time on in this paper that we read. So suppose we wanted to explain why Amir actually recovered from his strep throat and not just the probability. And the fact that he was given antibiotics should be part of that explanation. But it is not an exceptionless law that everyone who's given antibiotics recovers from strep throat, right? There's a high probability that they recover. But again, we want to know, can we explain an actual event, right? Amir's actual recovery, not a probabilistic claim. So this inductive statistical explanation, this is one important difference between that and the deductive, is that you can conclude an actual event, right, that is falsifiable. So how would that work, right? So you might think as a first pass, you could do a deductive argument like this. So the probability of recovery, given that you have strep throat and you're given penicillin, equals 0.95. Amir has strep throat and is given penicillin, therefore it is very likely that he will recover. But again, that's not what we wanted to explain. We wanted to explain why Amir did recover, not why he was likely to recover, right? We want a conclusion that can be falsified, right? This is sort of our Popperian intuition that this is very important for science. And Hempel, Oppenheim definitely picked that up, and they want to make good on that. And what Hempel says is, yeah, that's just the wrong way to think about this sort of inference. Um, so he says compare, like, it's like trying to do a similar thing with deduction, right? Like, what we don't do is we don't say, okay, all F's are G's, A is F, therefore it is necessary that A is a G, right? We don't put the probability or the necessity or sort of the strength of the conclusion into the conclusion itself. Um, the necessity is part of the inference, right? So all we conclude is that A is G, right? Um, and when we conclude that deductively, we know that it necessarily follows, but we don't have to also say in the conclusion it is necessary that, right? And that's, if you look back here, previous slide, that's kind of what we were doing. We were just pushing the probability into the conclusion when the probability is already included in the inference because it's an inductive inference, right? Um, so this is really what the inductive statistical explanation is supposed to look like. And he's got a double line here, right? So he says the probability part of it is in the inference because it's an inductive inference and not a deductive inference. And so that allows us to conclude just that Amir will recover, right? We don't have to pack any probability statements into that conclusion. So once again, right, we have the probability of recovery given that you have strep and antibiotics is 0.95. Amir has strep. Amir is given antibiotics. Okay, makes it very likely Amir recovers. But here's a problem. So that is an account of both kinds of statistical explanation. But Hempel recognizes that there is a bit of a complication here that he needs to account for. And he calls this the ambiguity of statistical explanation. So suppose that Amir has a strain of strep throat that is actually resistant to antibiotics. And this changes the probabilities, right? The probability of recovery in that case, if you have the resistant strain, is 0.05. So let's call that situation S star, right? Um, so we could describe the exact same situation differently and use a different argument, right? So the probability of recovery given S star, right, the resistant strain, and penicillin equals 0.05. Amir has strep throat, and I think that's wrong. It should be, sorry, Amir has S star, right, and Amir is given penicillin. And then you get the conclusion that Amir does not recover, right? Well, this is interesting. Now we've concluded, right, in both cases, the premises were true, right? And we did a perfectly good inductive inference, and yet we got RA in one case and not RA in the other case, right? Here's the other argument. Perfectly good, true premises, right? He did have strep. He did get penicillin. It is true that 0.95% of the time, people with strep that were given penicillin recover. So we have two perfectly good arguments, each of which has two premises, and yet we get contradictory conclusions. So you might worry, well, what good is statistical inference then, right? How can we trust that explanation if we know there's an equally good one that entails the opposite? So this then is the problem of the ambiguity of statistical inference. So how do we solve it? Now notice, let's diagnose the problem first. So this isn't going to be a problem for deductive explanation, right? So if you, in deductive logic, if you get contradictory conclusions, there's something wrong with one of your premises. You're going to have a false premise somewhere. And we had the different problem. We had true premises and contradictory conclusions. That can happen in inductive logic, right? Which is the whole problem. So Hempel diagnoses the problem in terms of what he calls reference classes, right? So a given event can be described as belonging to two or multiple different reference classes. So I might describe Amir's infection as simply a strep infection. That's totally true, right? It's just a description under one reference class. But I can also describe it as an antibiotic-resistant strep infection. That's also true. It's describing it in a different reference class, right? Described as one, um, then it falls under the law that gives it a 95% chance of recovery. Described in the other way, it falls under a different law that gives it a 0.05 chance. Again, both true statements, it's just how you describe the situation. Okay, so now it gets a little bit formal here. So Hempel says, take all of our scientific knowledge, be a set of premises, right? Everything we know, all the sentences from all our theories. Also, everything that entails, right? So all the conclusions that you could draw from those theories, those premises. Call that whole set of scientific knowledge K. So the problem is different subsets of K can be used in premises, again, all true, right? True scientific knowledge. But depending on the subset you pick, you're going to get different conclusions and you can get contradictory conclusions. Wait, only since K is supposed to be all our scientific knowledge, all the true stuff, only one of those conclusions will actually end up being in K, right? One of them will actually happen. They'll recover or it won't. So that means one of our conclusions will actually be false, which means that then we can predict, we're going to predict false stuff pretty regularly. That's not a good explanation. So how can we rule out these bad ones? Well, it's intuitively it should be obvious which one is the bad argument, right? The one that doesn't mention that the strain is antibiotic resistant, that's the bad argument. It's not giving us all the information we need. So what we need to fix this problem is we need to add some sort of condition that statistical explanation needs to use all of the relevant available evidence, right? It's just not good enough to tell us that people who are given antibiotics recover with 0.95 probability if there's more information that would be relevant that we would need to know, like if the strain is resistant to antibiotics, or maybe if the infected person is 105 years old, right? That would be good to know too. We need all that info. So this is called the requirement of maximal specificity, right? Good explanation is going to have to give us all the information. But importantly, we need the relevant information, right? If we ask for all the information, that would just be K. That would just be all of our scientific knowledge. So that wouldn't really be helpful. We need to narrow it down to what's relevant, and relevance is kind of a fuzzy notion, right? So how are we going to state that more formally? And what Hempel says is, okay, what I mean by relevant is we want the explanation whose probability statements pertain to the narrowest reference class of which the case under consideration is a member, right? So Amir's infection is a member of a reference class, right, bacterial infections, but it's also a member of an even narrower one called antibiotic-resistant infections. So in that case, we'll go with the narrower class in our explanation. So again, that's what I just said, right? He has an infection. There's a broad description of it, a broad reference class it belongs to. There's also a narrower one, and they have probabilities. So when the probabilities differ, use the reference class with the smallest membership, the fewest things in it, right? There's going to be fewer. There's the set of antibiotic-resistant infections is going to be smaller than the set of antibiotic infections overall. Right? And here it's important, right? But then you can compare it to situations where it won't be important, right? So like the half-life of radioactive element. So you could consider it under the reference class of radioactive element. You could certainly consider it under a narrower reference class, radioactive element in a room with 25% humidity, right? Radioactive element in a room that has a cat in it or whatever, right? That's going to be a narrower class, but it's not going to change the probabilities of decay at all, right? So in that case, you're fine to use the broader reference class, right? It doesn't matter. So, okay, now we're just going to, I think that's the idea, right, of the problem of the ambiguity of statistical explanation and that the requirement of maximal specificity can fix that. So now he's just going to state it formally. So he says, take a given explanation of B's being G. So here you have the probability of being a G given that you're an F is R, B is an F, right? And then we have our inductive double line, right, inference. So we conclude, okay, B is a G. So let's take both those premises and combine them into a single conjunction, call it S. And then make another huge conjunction out of our set of knowledge, right? And we'll call that K. If S and K implies that B belongs to a subclass of F, call it F1, then S and K will also entail the probability that the probability of B being a G, given that it's in a narrower class, F1, will have another probability, R1. And so the requirement of maximal specificity is that the probability R produced by the statistical law we end up using in our explanation should be equal to R1. Basically what that says is, again, pick the narrowest reference class with respect to the property that we're interested in. Of course, now this means that our explanation, whether it's good or not, is going to be relative to K, right? The entire group of our current scientific knowledge. And that's definitely going to change over time. It always has, and I'm sure it always will. So this means that explanations are epistemically relative, right? They're relative to our state of nature, our state of knowledge at a given time. Deductive nomological and deductive statistical explanations aren't relative in the same way. They don't have the ambiguity problem, so we don't have to invoke this K, right, in the account. But maybe that's a good thing for statistical explanation, and maybe that's not such a great thing for the deductive nomological account, right? Because we saw in the problems with the DN account, the Scriven paper, that it really turned out that explanation kind of is relative to a given context. Right? So maybe statistical explanation, right? Maybe it does sort of fix some of the problems we saw with DN. Right, well, that's it for now, and then the next lecture will be on statistical relevance.